Hello and welcome to today's lecture. So, in the last two lectures we had briefly discussed about two distributions, the T-test, the T distribution, the T distribution, okay, and the chi-square distribution. Okay. So, the T-test is used for when n is small. Okay. So, your z equal to x bar minus mu by s by root n does not follow normal distribution, okay, does not follow normal distribution. Okay. So, instead we calculate, so the same value calculated at s bar minus mu by s by root n is called the t value, and so as opposed to the normal distribution, the t distribution is much more flatter here with longer tails. Okay. So, this is your t distribution. Okay. So, the way of using a t-test, so the way to use a t-test, okay, is to look up the t table, okay, look up the t table where you have df and then various t values, okay, t of 0.1, okay, so t of 0.95, 0.05, so on and so forth. Okay. So, p of 0.1, so it is other way around, it actually starts from 0.1, t of 0.05, t of 0.025 up to t of 0.101. Okay. So, the t-test actually gives you the area for the upper tail only. Okay. So, for a t-test your hypothesis is mu equal to mu naught, right, and let us say your alternate hypothesis is mu is greater than mu naught. So, what you will do is you will calculate the t, you will have for given value of alpha you will calculate t of alpha, and if your t value is x bar minus mu by s by root n is greater than t alpha. So, this would imply that h naught is to be rejected. Okay. So, t is used for small sample estimating the population mean or differences in population mean. The chi-square distribution, okay, is used for estimating population variance. Okay. And the statistics that you calculate is used called the chi-square value, is given by n minus 1 into s square by sigma square. So, the chi-square distribution is asymmetric, it looks something like this. Okay. So, this is a f of chi-square and this is your chi-square value. Okay. So, for a one tail test, okay, you for a given value of alpha you calculate lambda square alpha. Okay. So, if your lambda square is greater than lambda square alpha, implying your hypothesis can be rejected. Okay. So, you can also use the chi-square distribution. Okay. You can use the chi-square distribution for a two-tailed test. Okay. In this case, okay, you calculate chi-square of alpha by 2, okay, and chi-square of 1 minus alpha by 2. So, if you choose, so if your lambda square, okay, is either greater than chi-square of alpha by 2 or less than of chi-square of 1 minus alpha 2, you accept your alternate hypothesis. Okay. So, the confidence interval, okay, the confidence interval for lambda square given for a two-tailed test. So, your 95% confidence interval is given by n minus 1 okay. So, if you choose alpha equal to 0.5, so your alpha by 2 is going to be 0.025, okay, and okay. So, if you choose alpha equal to 0.025, then this value is going to be chi-square of 0.25 and this is chi-square of 1 minus 0.025. Okay. Based on this, you can calculate the 95% confidence interval. Now, let us say instead of estimating population variance, you want to estimate or probe the difference of two population variances. Okay. So, in this case, so you want to compare population variances. Okay. So, your null hypothesis is sigma 1 square equal to sigma 2 square. Okay. And in this case, you draw. Okay. So, if you draw random samples from two normal populations, with equal variances, okay, then the metric S1 square by S2 square has a probability distribution called the F distribution. Okay. So, your F distribution, this is the metric F, and the F distribution looks something like this. Okay. And the peak is corresponding to F equal to 1, that is when both the population variances are same. Okay. And you would do a single tail test for an F distribution just like you have done for all the other case. You will take the value of alpha, which is the area under the curve, and find out what is F of alpha. Okay. You will find out the value of F of alpha. So, how does a F table look like? Okay. So, in an F table, okay, you have two metrics. So, you have drawn a sample from, so you have sample sizes of n1 and n2. Okay. So, you have 2 degrees of freedom. Okay. One is df1, which is n1 minus 1, and df2 is n2 minus 1. Okay. So, in an F table, you have the values of df1, okay, you have the value of significance and df2. Okay. So, for example, in df1 you will have various values, let us say 1, 2, 3, 4, so on and so forth, and A will have various significance levels, let us say 0.1, 0.05, 0.025, and so on and so forth. And for each of these you will have df2. So, this is one value corresponding to df2 equal to 1, you have these values of A. Similarly, corresponding to df2 you will have various other values of A. Okay, so these are your significance levels. So the way to look up the table is find out what is df1, find out what is df2, and see corresponding to the value of a at the desired level that you want, what is the value of alpha. Okay. So for example, if my df1 was 1 and df2 was 1 and my significance level was 0.05, then this is the value I will choose. So you have values written for all of this. Okay. So all of this you will have corresponding to each combination, you will have values specified. Okay. So let us take a sample example. So imagine, okay, so imagine I have n1 equal to 10, s1 square, okay, equal to 7.14, okay, n2 equal to 8 and s2 square equal to 3.21. So what is the value of f, and whether I want to calculate whether f is significant or not. Okay. So I have defined f as s1 square by s2 square is my test metric. So in this case it is simply 7.14 by 3.21, and you get a corresponding value, okay, of f equal to roughly 2.22. Okay. Now for significance level alpha equal to 0.05, okay. So if when I am doing a single tail test, okay, so if let us say my hypothesis, so my h naught is sigma 1 square equal to sigma 2 square, and h a, okay, is sigma 1 square, okay, not equal to sigma 2 square, then what I have to do, okay, for this curve, okay, f, I find out alpha and the corresponding value of f of alpha. Okay. So if I so I have two values. So if my alternate hypothesis is sigma 1 square not equal to sigma 2 square, I want to find out the value of f of alpha by 2 corresponding to alpha by 2. Okay. So this is for two-tailed test. So for alpha by 2, in this case alpha by 2 is equal to 0.025, you will look up the value of f of alpha by 2 corresponding to df1 equal to 9 and df2 equal to 7. 9 is 10 minus 1, this is 8 minus 1. So this f of alpha by 2 is 4.82. Okay. So I can reject my hypothesis if this value f calculated as 2.2 is greater than f of alpha by 2, but in this particular case 2.22 is less than 4.82. So this means I cannot reject h naught. Okay. So you can also find out the confidence interval . Okay, for sigma 1 square by sigma 2 square. Okay, and that is given by the following bounds. You have sigma 2 square okay. So what you see are two different terms, s1 square into s2 square into 1 by capital F of df1 comma df2, okay, and the other one is f of df2 comma df1. Okay. So if we go back to the table, okay, if we go back to the table, let us say if I had a df1, say for example, if my df1 was equal to 4 and df2 equal to 1, so 4, 1 with a significance level of 0.05, and if I am doing a two-tailed test, this is the value I would be looking for. Okay. So, for two-tailed test, okay, this is my f of df1 comma df2. Okay. So, correspondingly I can find out f of df2 comma df1. So, df2 is the corresponding value. So, in this case df2 is 1 and 1 comma. So, I can accordingly write, let us say for 4 I will have various values. So, this will be f of df2 comma df1. Okay. So, you can have two different values and the expression gives you, okay. So, and the expression gives you 1 by f of df1 comma df2 or f of df2 comma df1. Okay. So, for example, for the case that we discussed right now, for a 90% confidence interval, okay, you can look up f of 9 comma 7, this is 3.68, okay, and f of 7 comma 9, this is 3.29. Okay. So, your ranges for this case, okay, you had S1 square, for this case you had S1 square 7 1.14 and S2 square 3.21, right. So, that is why you got df1 is 9 and df2 is 7. So, for this particular case you can calculate the lower and upper bounds of sigma 1 square by sigma 2 square as 7.14 . So, this comes out to be 0.6 less than sigma 1 square by sigma 2 square less than 7.32. So, you see that your bound is reasonably wide, that is why you have been unable to reject H naught. Okay. Okay, so, even though you have been unable to reject H naught, your variance is, the ratio is quite variable. Okay. So, that brings us to end of our discussion on T-test and F-test for difference of population means and population variance. What we will initiate now is our discussion on a very important aspect of statistics called analysis of variance. Okay. Or in short, it is referred to as Anova. Okay. So, in Anova, so why are we interested in analysis of variance? So, let us say you want to calculate, okay, you have cell phone users, okay, and you want to look at their data plans that they sign up for. So, cell phone users can themselves be distributed as users using expensive phones, expensive maybe smartphones, and users using simplest phones which are not smartphones. Okay. So, if you were to calculate the variability in the data plans that people search out for, you can clearly see that there will be reasonable variability, because people who use smartphones, they sign up for data plans, they have expensive data plans, versus people who use simple phones, their usability is only dictated by having a phone connection. Okay. So, you will have huge amount of variability when you compile the statistics for data plans. So, to address it, how can you make a plan, or when a company is thinking of what should be its pricing strategy, it should take into account the inherent variation in the population. Okay. And analysis of variance is that metric, is that procedure which allows us to incorporate what is the effect of a subpopulation on the variability of the overall population. So, you try to assign the variability into individual factors which are likely to have distinct effects on the overall variability of the statistics that you are measuring. Okay. So, as a consequence of which, when you want to compile the statistics, you have what is called an experimental plan. Okay. Experimental plan or experimental design, or it is also called the sampling plan. Okay. So, this is to account for how should you actually set up the experiment. Okay. And when you are thinking of experiment, so for any experiment, okay, so there are various aspects of the experiment. First is who are you measuring it on, or what is your experimental unit. Okay. So, if for example, in the case of cell phone users, your experimental unit can be just the population of users. Okay. Second is the factor. Okay. So, in the example that we discussed, the factor can be whether they are smartphone users or not. Yes or no. Okay. You will have a setting. Okay. So, setting is a value or the intensity scale of the factor. In case for this particular example, my setting is simply yes or no. Okay. And you have the response. This basically whatever is your metric that you calculate from the statistics. Okay. So, let us take another two examples to discuss, to clear these ideas. So, imagine that a group of people have been divided into an experimental group and a control group. Okay. So, the control group, so I will write CG for control group and EG for experimental group. So, your CG is given an aptitude test after breakfast, versus the experimental group take the test without breakfast. Okay. So, let us identify each of the things that we said. So, what is my experimental unit? Okay. The experimental unit, okay, in this case is just people. It is nothing, people who are taking the test, both the experimental and the control group. What is the factor? Factor is your breakfast or meal, because you want to probe the effect of meal. What is your setting? Okay. Whether it is yes or it is no. Okay. So, your treatment or setting is both the same, because treatment is either they have had the breakfast or they have not had the breakfast. And what is your response? Is your score, aptitude score. Okay. Now, imagine in this same population, Okay. So, in the same population, so earlier I had, so earlier I just had people. Okay. Now, I have men versus women. Okay. So, now in terms of treatments, okay, treatments can be men with breakfast, men without breakfast, okay, women with breakfast, and women without breakfast. Okay. So, now you have, instead of 2 conditions, you have 4 cases, 4 combinations. Okay. So, depending on your experimental plan, you might have many more experimental combinations. Okay. With that, I thank you for your attention, and we will stop here. In the next class, we will continue with our discussion on ANOVA.